Thank you. Hello, everybody. So I'm Luca Sassoli de Bianchi, and I'll be presenting this experiment, which I conducted together with Massimiliano Sassoli de Bianchi. First of all, I have a confession. I'm not a physicist. My domain of expertise is more linked to design, art, and computer programming. So this is a good example of an interdisciplinary work, and as well as an interfamiliar one, as you might have noticed through the shared family name with my co-author. So let's begin. The field of quantum cognition has shown many analogies between how... Everybody can hear me? Or you want a mic? No? So the field of quantum cognition has shown many analogies between how quantum systems behave and how cognitive systems behave as human. Sandro this morning showed us some powerful example of that. And taking those analogies very seriously, in 2009, Gideric Arts put forward the hypothesis that the fundamental nature of quantum entities could be indeed a conceptual nature. This hypothesis has been then formalized in the conceptuality interpretation of quantum mechanics. Our experiment aimed at exploring some of those ideas. How did we do that? Well, we devised a cognitive transposition of a very famous double-slit experiment and the less known but equally important triple-slit experiment. What we found are many similarities and some difference between how quantum entities interact with measurement apparatuses and how human concepts interact with human minds. So first of all, I need to give you some context. I'm sure a lot of you are very familiar with this very famous experiment, and one of the surprising aspects is we have a single slit situation and we see the impact on the screen, and our, let's say, classical intuition would imagine that when the two slits are open, we would just see a uniform average, while what we see in the laboratory is the famous interference pattern. And one thing to point out is quite surprising, because the classical uniform average predicts almost no impact in the middle, while it's exactly the opposite of what we observed, with these quantum entities. Another important thing to remember is that this is not interference due to a collective nature of all these particles going together through the two-slit experiment. No, even when we send just one entity at a time, through time we see one impact after the other building the interference pattern. So this truly means that even a single entity, when it interacts with a detection screen, it's doing so in a localized fashion, like a particle. But again, a single entity, when it interacts with the two slits, is doing so in a non-ondulatory fashion. So it means this single entity has this two nature, like a wavicle. But can we really say that an entity has two incompatible nature at the same time? Of course, it seems not. That's why it's interesting to search for what could be the underlying nature which could explain those mechanisms. The conceptuality interpretation postulate that this could be a conceptual nature. This could have the power of explaining that. Now, I have to precise, when I say conceptual nature for quantum entities, I'm not saying that quantum entities can be mixed with human concept, that they are the same thing, or those are very different entities, of course. And I think a good example of what is being said here is to think now we are in Tropea, there are beautiful sea waves in the sea, and now you're also looking at the presentation, your eyes are using the electromagnetic waves to see it. Those two wave phenomena are completely different entity, but they do share an underlying nature and some underlying mathematics. So it's more this idea I'm referring to. This experiment is done for the first time in the 1800 by Young and has been repeated countless times with photons, electrons, neutrons, and also large molecules. Now, what could be a cognitive equivalent of this experiment? For this, we can look at an experiment done in the 80s by psychologist James Hampton. He asked his student to rank, according to different categories, 24 exemplars of food. The categories were fruit, vegetable, and fruit or vegetable. So they ranked them in order of typicality for each given category, and then he calculated the probability of each one of those exemplars to belong, to be associated with those category concepts. Here we see the probability plotted, and in blue for fruit, in green for vegetable, and in a brown line for fruit or vegetable. Again here, what James Hampton immediately saw our normal intuition using logical, classical reasoning would tell us that the probability of belonging to the combined category, fruit or vegetable, should always be higher than just fruit or just vegetable. But as you can see here, the probability curve for fruit or vegetable is almost always lower than one of the other two curves. So what is happening inside the reasoning of those collective cognitive mind of a participant must be something different. A good way of looking at it is to think that the combined category with a disjunction fruit or vegetable for the participant is representing an expression of doubt when trying to associate it with just fruit or vegetable. To give a clear example, you can see here, for example, elderberry, which is a berry, so clearly a fruit, score very high in fruit and quite low on vegetable, doesn't create much doubt, thus its association with fruit or vegetable is fairly low. While something that is clearly a good example of doubt, like mushroom, is mushroom a fruit or a vegetable, clear expression of doubt, score quite low for both category individually, but much higher for the disjunction. See?
The participants could select only one answer.
So no, they had to give a score for a typicality score for, like, they have an exemplar and they would say how much these belong to fruit. Then in another moment, how much these belong to vegetable, and then how much these belong to fruit or vegetable. Yes. So it's for all the exemplar they had to give this different ranking. And you may say, this is very interesting, okay, on a cognitive level, but why this is a representative for the double-slit experiment? Well, you could see the following analogies. You could take the fruit and vegetable concepts as being the two slits. You could take the exemplars of food as impacts on a cognitive detection screen. So choosing a good exemplar for fruit means choosing a good example of an impact of an entity coming from the first slit. Choosing a good exemplar for vegetable means choosing a good example of an impact for an entity coming from the second slit, with only one slit open. While choosing a good exemplar for fruit and vegetable is like choosing a good example of an impact on the detection screen when both slits are open, so in the interference situation. Of course, Hampton was not thinking in terms of quantum physics at the time, he was a psychologist, but we can see some further interesting analogies when Diederik Arts later took Hampton's data and tried to use quantum mechanic formalism to model them. So to do so, he started by using a two-dimensional detection screen. The exemplar live in this two-dimensional space of potential exemplar. He places them and then use Gaussian wave function to model the data, and projecting the probability of those functions, he can then map the data for just fruit and just vegetable. As you can see there, the points are the exemplar and the brightness is the probability. As you can see here, for fruit is centered on apple, for vegetable is centered on broccoli. Again, if you follow a more simpler classical intuition, we could say, oh, we can just do the average of the two and we would obtain this. This, of course, does not map Hampton's data for fruit or vegetable at all. But if instead we do the superposition of a two-wave function, as Diederik Arts did, and then we project the probability of the superposition, we can obtain this interference pattern, this birefringence pattern, which does manage to correctly map Hampton's data. So this means that the formalist can model this human cognitive behavior quite well. Again, in the conceptuality interpretation, these peaks and valley of probability can be interpreted as places which maximize or minimize the doubt about this association. Okay, so this was for two slits. Let's add one more slit and go to triple-slit experiment. What happened in physics laboratories? Well, there we have pretty much the same situation in what we observe in the detection screen. The peaks are in the same positions. The central peak is also the one of maximum intensity, and we just see some secondary peaks appearing at the valleys. Of course, if all the experimental settings are the same, distance, the slits width, so on and so forth. What is a bit more interesting is to look at the mathematics behind the triple-slit experiment. A common way of proceeding would be to express the wave function for the three-slit situation as the superposition of a wave function for the single-slit situation. And then we can simply use the Born rule to get to the probability, and of course the probability are equivalent to the brightness, the intensity on the detection screen. And to do so, again, we just take the square module of a wave function, doing some calculation, we arrive to a first contribution, which is like the classical average of a probability for the single-slit situation, and then an interference contribution. First thing to notice that is interesting is that the interference contribution for these triple-slit probabilities is only expressed as contribution of interference of a two-slit situation, so second order contribution. This is because the Born rule is quadratic in the wave function. So that's already interesting. There are no genuine third order interference contribution. So we can again do some calculation and express everything in terms of probability, and we could have then this expression equal to 0. This is what experimental physicists call the Sorkin parameter. And this parameter seems to be predicted to be 0 by the Born rule. So experimental physicists were very happy. They have a measurable value that they could use in experiment to test the validity of a Born rule. And of course, not only quantum mechanics, but also classical mechanics predicted to be 0, as it can be expressed just in terms of interferences. Now, this is interesting, but is it generally true? Is it always the case? Well, actually, it's a bit more complicated, because our first assumption that the wave function of a triple-slit situation can be expressed as a superposition of a single wave function is incorrect. We can see this in different ways. One way is to look at Feynman path integral approach, which tells us to consider for the final probability all the possible paths the entity could take. And if we take this seriously, we can imagine paths which pass through multiple slits at a time, looping back, touching more than one of them. So of course, those paths will contribute less to the final probability, but they are present nonetheless. And of course, how can we associate a path touching the three slit to the wave function associated for just a single slit? We cannot. So if we do that, we are ignoring those paths. Another way of looking at it is that when the experiment for the triple slit is done, we have a mask covering the slit and just choosing 1, 2, or 3 of them. And we move the mask to calculate the probability for single, double, and triple. When we move the mask, we are changing the experiment settings. We are changing the Hamiltonian. So these 4 wave functions up here have 4 different Hamiltonian associated to them, and we cannot just naively put them in the same equation. So actually, no, the Born rule does not predict a 0 Sorkin parameter. But we can intuitively see that perhaps it's very small. And later initially experiments were finding this 0 Sorkin parameter, but later on, making them more precise and calibrating better, they did find non-zero Sorkin parameter in the triple-slit experiment. Okay, so this is all the context I think you need. This was a triple-slit experiment in physics laboratories. How does it look in cognitive laboratories? And this is exactly what we did with Massimiliano. So, our experiment. It was an interactive experience running from a month, the 6th of March of this year. We had the fortune of having 213 participants. Each participant were presented with 7 sub-experiments, 3 single-slit, 3 double-slit, and 1 triple-slit one. For each one of those experiments, they had to answer by choosing a cell on a detection screen. And they actually give their 7 best answers to every question. We later then assign the different points, a scoring system to those answers. This allows us to have almost 6,000 effective data points for each experiment. And the average duration was a bit more than 9 minutes. So those are the generalities, but what was this cognitive situation we presented participant? We wanted to have something as similar as possible as the triple-slit experiment. But we didn't want to be too explicit to avoid any kind of bias for people who maybe know this kind of experiment, and also we wanted to keep it as essential as possible. What we did is the following. We told them to consider a big field. On one side of the field, there are 43 identical portions of food. This is our detection screen. On the other side of the field, we had a wall with 1 or 2 or 3 openings. The participants were told that an animal will emerge from one of the openings. The animal will then move in a very undefined way through the field, and at some point, it will reach one portion of food. Once the food is reached, it will be eaten and the animal will go away. It is really emphasized to the participant that the nature of animal is completely unknown, the way it moves is unknown, and the way, if he can perceive the food or not, is unknown, and which senses he may use, we just don't know. So a great situation of just of doubt about what mechanism is at play here. Then, for the different experiment, we ask the following question. In the single opening experiment, we told participants to motivate them that they bet a large sum of money to try to guess what portion of food the animal will eat. So they choose the portion, the cells on the detection screen, picking their 7 best answer, and moved on. So this was the simple case. Now, when we have multiple openings, we have a new layer of doubt because we don't know from which opening the animal may emerge. So the question to the participant has changed. We ask them now to consider an imaginary opponent. The opponent will look at a situation and see which portion of food have been eaten. The opponent will have to guess from which opening the animal which ate the food came from. The participant instead, he can choose the portion of food eaten, and he will choose it to make the life of the opponent as hard as possible. They try to make the opponent fail and not guess from which opening the animal came from. Another way is to say participant had to choose the portion of food which maximizes the doubt about from which opening the animal came from. So a point of doubt maximization about the source. For the triple-slit, triple opening is the same situation. And that was the experiment, very simply. We then collected the data and we could calculate very easily the probability. We just take all the points assigned to one cell and divide it for all the points assigned to the whole screen. We obtain probability for single slit situation, double slit situation, and triple slit situation. And the fact that we had all these probabilities allowed us very easily to calculate the sorting parameter as well for a cognitive experiment. Here we calculate a normalized sorting parameter so we could compare it with sorting parameter from physics laboratories. And now we get to the fun part. We can analyze the data. So here the representation is, here is basically the slit plate with the openings in the different position. I didn't tell before, but of course the order with which participants see the different openings was randomized to avoid order effect. Here we plot the probabilities of a specific cell on the detection screen to be chosen. And here just the same probability, but as an intensity, a bit reminiscent of a detection screen, a one-dimensional detection screen. For the single slit situation, this is quite similar to what we would see in a physics laboratory. Nothing too strange here. We can understand why participants choose right in front of the openings, easy interpretation. In the two-slit situation, we see some more structure emerging, and this structure will be even stronger in the triple-slit data. First of all, we see a central peak of maximum intensity. Central meaning in between the two slits. And this is what we see in physics laboratory. And is also what is expected following the conceptuality interpretation of, because this point of symmetry, of course, through the symmetry of the two slits, it maximizes the doubt. That's quite evident. But we also see, again, it is a bit more shy, but secondary peak forming. And they're a bit more strange because, I mean, it's not the conceptuality interpretation also hypothesized could explain the appearing of these secondary peaks, but it's strange their position because they're right in front of the openings. And this, of course, seems a point of minimization of doubt. And we don't have an explanation for this, but it's important to remark that in the cognitive setting, people are not using only simple, logical, analytical reasoning in the answer. We have this structure which does appear across all participants, which is very strange. Then we also see an edge accumulation effect. People place points at the edges, at the extreme, trying to go as far as possible from the openings. We can see this also as a strategy to which maximizes the doubt. If you imagine that you have two houses right in front of you, they're very big, it's easy to distinguish, but if you go many kilometers away, the two houses start to merge and become a single point. So this is a way to lower discrimination and increase doubt in the situation. So again, a viable strategy. This is the three-slit situation, and again, we have the same thing. In between openings, peaks of maximum intensity, secondary peaks in relation to the opening themselves and the edge accumulation situation. A little mention, there is a bit of a left bias here. The left side of the detection screen seems to be preferred. This could be because participants came from a left to right reading culture, so it's an hypothesis, so they prefer lefty choices. Now let's go a bit more in depth about analyzing this data. One thing, if we compare it to the physics laboratory, is to remark that the central peak for the triple-slit experiment is not the one of maximum intensity. Okay, well, in the physics laboratory, it is the one of maximum intensity because the symmetry makes it so that in the central point, the wave function always interferes with a maximum with maximum the most constructive way. It's not our case. We don't have the same mechanism apparently, but we try to reason, and we also have a mechanism not based on wavelength, but on length. Our hypothesis is the following. What I'm going to describe could be one of the reasoning that subconsciously or consciously was part of the answer of a participant. We have to think first that the distance between a portion of food and an opening is like the probability for the animal to come from that opening is inversely proportional to the distance between the point of food eaten and the opening. So participants look at the whole portion of food, and for each one they look at the distance between the three openings. And then they look to maximizes the smallest distance of a tree. If we plot this reasoning on the graph with this formula, we see this, the black line. Here the red is just the same probability we have here but plotted on the other graph. And we can see that some of the structure is represented by this more hypothetical length reasoning. We have the peaks of maximum intensity in correspondence to the midpoint. We have a second high point in the middle, then it decreases and it increases again with the edge accumulation effect. So this is very nice. This could be one of the many ideas in the collective mind of the participant. Another worry we had was, what if our scoring system that we give was creating this structure? Because we give an arbitrary scoring system. We say, oh, first choice is 7 point, then 6, 5, 4, 3, 2, 1. What if this arbitrary choice is creating the structure, the nice structure I'm presenting now? So we try other scoring point. We try an exponential descending scale. We try to only consider their single answer, and we try also to use an uniform scale where every answer just gets 1 point. Luckily, as you can see, the structure is preserved. Actually, in some cases, even just the peak are a bit accentuated. And even with just 213 data points where we take just the first choice, the structure is appearing. And this is nice because it's a bit more similar to what happened in physics laboratory. You don't ask your detection screen to give its 7 best answer when detecting an impact. It just gives you 1 impact. All right, let's also look at the sorting parameter. Here it is in blue, compared to the probability for the triple-slit experiment. In physics laboratory, we find normally 10 to the minus 3 or 10 to the minus 2, the maximum sorting parameter found in those triple-slit experiment. But there also have been experiments which found a sorting parameter of a magnitude of 0.35. This is when they use near field effect or microwave domain to amplify this value. We found 0.549, so quite high. Actually, using the other scoring parameter, we can even go higher. What this could mean? Well, as you remember, it means that there are genuine third-order interference contribution to our situation, and this could be interpreted to the fact that participants were not looking at a situation of a 3-slit just in terms of 2 slits at a time, but they were generally considering the 3-slit altogether. So, in summary, we found many similarities and some differences between what happened in physics laboratory and in this cognitive laboratory. For example, it was indeed not obvious, like we found a central fringe of maximum intensity, and it was not obvious to see also these secondary fringes also appearing. This means that the human cognitive mind does have the richness necessary to create those structures, which kind of further indicate the possibility of the conceptual of the fact that the human mind can have a shared nature with this supposed conceptual quantum entity, so bring forward a conceptuality interpretation. We also see some differences. We don't have this central fringe of maximum intensity for the triple-slit situation right in the center. And also, I haven't explained it here, but we couldn't associate any obvious effective wavelength in our experiment. And of course, we can interpret this was a bit expected. We know that the human mind is much more variable than experiment in quantum physics laboratories. And one interpretation for this variability, if we do different cognitive experiments, we have more variable result, is the fact that even if the physical universe has this cognitive conceptual nature underlying it, it's very old, and it had almost all the time we know of to stabilize and construct itself, harmonize. While human culture and human concept are very new, just very early development, and so perhaps they are more in an unorganized, more chaotic state, and perhaps they will evolve and stabilize themselves. So, in conclusion, our cognitive triple-slit experiment adds to our understanding of how human mind deals with situations of doubt, and it further pushes the explanatory power of the conceptuality interpretation, an interpretation which is still, of course, under much investigation by the Brussels group. Thank you very much, and now I'll take any question. And if you want to join also for the question time.